I left some parts in this lecture 6, that is yesterday's lecture, incomplete. So I still wrote those notes in the lecture 6 only. So that we will do it now first and then start affine groups. So why do I want to do that? Because I still want you to understand affine maps a little bit better. And remember one thing, this is a mixture of geometry and algebra, and it always happens. Geometry is sometimes hand waving, and the algebra makes it more precise there. And whenever things become more precise, generally people feel it is difficult. Geometry can wave hands, but this I'm mixing algebra and geometry. I'm mixing group theory and elementary geometry. Have you had a look at Sonakshi again? Have you had a look at the supplement I said last time?
Yes, sir.
And
Not the full one, but yeah, I have done the starting.
so are you comfortable?
Yes, sir.
And did it remind you your school days or college days?
Yes, sir.
What probably it was different names, vector algebra or something like that.
Yes, sir.
All right. So shall I start now? Because again, otherwise we will have trouble to finish it. All right. So affine maps you have understood. It's a map which makes this diagram commutative. So it is, in other words, it is compatible with the operations of E over V and F over W. All right. So now I am going to list some basic properties of these affine maps. So ultimately, we want to compute, we want to list all the affine maps and how are they, how close they are to the linear maps. That is what the idea is. Because ultimately, I am going to take all affine isomorphisms and relate it to the automorphism group of a vector space. That is the aim. All right. So affine maps, as you know, that they are denoted by the pairs F0 and F. F is just a map from the set E to set F. Think of set E as points, and V is operating, additive group of V is operating on E, simple transitive. So therefore E has to be non-empty. There is no affine space which is empty by definition of a transitivity. And that F naught is a linear map from V to W. And how is it defined? That this is the defining this pink here, f of x plus p equal to f0x plus fp for every point p in E. And any other point will look like some vector plus p. If I fixed a point, any other point will look like x plus p. So f of q will look like f of x plus p, and then this is the formula. But again, if I want to get back in terms of q, then that this equality simply means this vector f naught x is a vector from fp to f of x, f of q. And that is unique. So this formula tells you, first of all, this one. What does one say? The linear part, f naught, is uniquely determined. And that is therefore called the linear part of F. I wrote the proof also. If X is in V and P is in E, I said let. So P is, as I said, E is definitely non-empty, therefore there is at least one point, that is P. And X is a vector space, so therefore definitely there is a vector. Maybe it is 0, but there is a vector. Then by definition, f of x plus p, which is q, which is f naught x plus fp, that means this x is uniquely determined by the images of that p and q under f, the arrow. So it's uniquely determined. All right, now the next one, for points p naught, I started with any point P0 and then took its image under F, that I call it Q0. That Q0 is a point in F. And then I say this diagram is commutative. E to F, that given map F, V to W, that is the linear part of F, that is F0, and the vertical maps are just the translation maps. X going to, see this vertical first map is X going to X plus P0, makes sense. W going to Y plus, Y going to Y plus Q0, that makes sense. So these are the maps. In fact, I am saying these are also affine maps. So how is thought V a affine space over V? That addition in V, that will give an affine structure of V on V. And with that, this is clearly affine maps. And what are their linear parts? Their linear parts are identities. All this follows directly from this definition. So you have to take this page and stare at it as long as you understand. All right, so that is, therefore, what did we check? For any point P0 and Q0, where Q0 is the image of P0, such a diagram is commutative. This is very closely related to the vector spaces, and that we will see that it is. And how do you check this? I said here, remember that V is an affine space over V by the addition operation on V plus. Remember, you don't have to understand anything. You have only given a V plus vector space, and we are only operating the additive group of V on this set of points E. And the very concrete example is with you, and we are adopting the same notation as in the example. That drawing an arrow above PQ. So like this. Do I have it here? Here, look here. And this, for this, I have said read the supplement as 0.5, S15 and S16. All right, the directions are also very important. If you change the direction, it will be the negative. That is built in this. All right. So that was the second point. That this diagram is commutative. And in this diagram, these vertical maps are bijective. That is because the action is transitive and simple. So given any other point, I can always find a vector x which joins that point P to P0. That means the map is surjective. The map is injective because that x is uniquely determined. So it is so neatly built up in the definition of an affine space that nothing is wrong. So natural. All right. Now the third one, if F is injective, respectively surjective, respectively bijective. There are three statements there. If F is injective, then the linear part is also injective. If F is surjective, then the linear part is also surjective. If F is bijective, then the linear part is also bijective. And what is the proof? Immediate from the above commutative diagram. See here, this is a diagram, and I am talking about the injectivity of F and injectivity of F0. So if F is injective, this diagram is commutative. So therefore, this F followed by this bijective map is also bijective. And if that is bijective, this F0 is injective. See here, if somebody goes to 0, you lift that up, and that will go to a unique point. So it just follows from the commutativity of the above diagram with the very good, the vertical arrows are bijective. Therefore, whatever property of F has, that property of F0 will have. In fact, the other way also. All right, so is that clear? So if F is bijective, if it is both injective and surjective, then the linear part is also injective and surjective. That means it is bijective. Okay, now 4 is little bit more. What does 4 say? If the linear part is bijective, then the inverse map. See, then we know that f is also, so this is actually if and only if statement. This I forgot to erase that and say if and only if. So I will do it now because otherwise I will forget. So these I erase and this, then I erase and then I write if and only if. All right. So if it is if f naught is bijective, then no, this also not is not there. So such writing mistakes will happen. If f is bijective, then so f is an affine map and it is bijective. There it's written on the top. It's an affine map. So if it is bijective, then the inverse image f inverse exists. Then this is also an affine map. It's like what you have checked such a thing earlier. If f is a group homomorphism from one group to the other group, and if it is bijective, then the inverse image of that inverse map of f is also group homomorphism. Isn't it true? Yes, please.
Yes, sir.
It's true, no? So similar to that, if f is bijective, then the inverse map of f is also an affine map. And what is the linear part of that affine map? The linear part of that affine map is precisely the f naught inverse, because f naught is a linear map which is bijective, because f is a affine map which is bijective. That is what we checked in these three, and therefore actually here we only check this way. So why unnecessary write extra things? So in this I only check this implication. All right, so is that clear now what properties of the affine maps you have learned? They are very closely related to the linear part of that affine map. And this book is again written here. And it's very easy. You please read it. Each word by word, line by line, you read it, and if you have difficulty, stop. And think for a minute. And what will help you? Understanding the definitions correctly. No other mathematics is used in this. No other prerequisites are needed, but for the definitions. All right, now the next definition. See, I am up to the defining that group, affine group. All right, so now we have E and F affine spaces or vector spaces V and W. Then bijective affine maps are called affine isomorphisms. Because already inverse is also affine. That is what we have checked above. And now if I take E equal to F, the affine automorphisms of E is called affine collineation, or it is called an affinity of E. All right. So if you have E equal to V, then it will be just automorphism of the vector space V. But it is not just G homomorphism or G isomorphism, because G is only the additive group of a vector space, and here we are demanding it is linear, so we are demanding more for a vector space. All right. So and then you collect all this AE, all affine maps from E to E, affinities. That means bijective affine maps from E to E. Those are affinities. And obviously, this is a group under composition, because composition of affine maps is affine again, and composition of bijective is bijective. Therefore, it is a group under composition. That means it is a subgroup of the permutation group. Not all permutations are affinities, but those permutations are affinities which are affine maps. And now that's what I said. Note the difference between AE and OT E V plus. See, this OT E V plus, they are maps from bijective maps from E to E, which only respect the group action, that is V plus. But here we are demanding more. We are also demanding they are linear. That is the difference. So therefore, this is actually smaller. So that is why you need more attention to this. This already we have computed. This was precisely what I showed you. See here, we did it even more. And this is a very nice, see here. This is the automorphism group of homogeneous G spaces. We actually did it not only simple transitive, but any homogeneous space, any transitive action, we computed that group of automorphisms. And that is precisely AGH mod H. But in our case, the group is commutative because it is V plus. And then the answers are easier. So the answers are easier in that case. So H will be trivial, and then there is a note there. Here I have written some note so that actually more is done. This group is understood well. So I will use my pen. This is understood better, that we already know from last lecture. But not this. And all that we know right now from the definition that this group is very closely related to the automorphism group of a vector space. And that is what I want to come to. All right. Now the next couple of remarks also I added in these lecture notes only. So anyway, I have sent both these things to Pawan. Now you will get it. So these also just a preparation. There are two, three remarks which I will go through quickly, and then we will go to our lecture. All right. So what remarks I am making? That I will tell you briefly. See, like if I want to produce a linear map from one vector space to the other vector space, what are the ways? How can I produce? Suppose I have a vector space V and I have a vector space W, and I want to produce a linear map from V to W. What do I do? This is your linear algebra. You would have studied it long time. So can somebody answer? How do I produce linear map from a vector space V to the other vector space W?
Through basis elements.
Sorry, who is answering?
Asaruddin, sir.
Your voice is splitting. I don't know who is talking. Yes?
Asaruddin, sir.
Azaruddin, tell me, how do you produce linear maps from one vector space to the other vector space?
Through basis elements.
Can you be a little bit more precise?
I will
You are
map.
correct. You are correct, but you have to tell me a little bit better way.
I will map each. Anyway, every element of the vector space can be generated through basis elements.
What is the basis element? One or many?
Many will be there, sir.
So what does that mean? Make a precise statement.
If my vector space has n basis elements.
And that you know it exists.
Yes, sir.
Right? So if what do you do? What you are saying is take a basis of a vector space.
Yes, sir. We will take a basis of vector space. Then for each basis element, we will map it to the basis element of the W space.
Basis element of W or arbitrary will do it?
Arbitrarily also we can do, sir.
All right. So what you are saying is all linear maps you can produce that way. You fix a basis of V and map each basis element of this given basis to arbitrary elements of W. And
Yes,
then you
sir.
get a unique linear map.
Yes, sir.
So therefore linear, so the first theorem you need to prove in linear algebra is every vector space has a basis. And once you have a basis, you can produce many linear maps. So now here also I want to do corresponding thing. I want to produce many affine maps. And for that I will have to do something, no? But I will have to reduce to the vector space. And this information what you said. So now read the proposition. E and F, two affine spaces or vector spaces V and W. Then a map F from V, F, E to F is affine if and only what happens? If and only for a point P naught in E, the map, the corresponding linear map, corresponding map I am defining, F naught x equal to this is linear. Now, if it is affine, it's a part of the definition that this F naught is linear. Converse is more important. So suppose F naught is K linear. Then I want to prove this map F is affine. What do I have to prove? That means I have to prove such an equation. F naught FQ equal to this. No, this last heading. And isn't that a definition of affine? Look here, affine. This is the equation. This means the map is affine for any P and any Q. So now here, look here. What I have written? I have taken arbitrary point P and Q and then this equal to this. I wrote something by this picture. First I defined by definition of the map F, FP is this. Why by definition? Because you see, look at the picture. P naught is given to me. And the definition of F naught is also given. So this is P naught, P vector is that X, then P is this, that is how we denote, and then F of P is given this. This is F naught definition. Here, F naught of P, F naught of this equal to this vector. That was the given definition. And then now you take arbitrary points P and Q and you write it from in this diagram. So this diagram says that if I take this vector and add this vector, it is this vector. That is what I use. That is what I have used. This. And therefore this. So therefore this shows that F is affine. And not only that, this F0 is a linear part. Now I want to be sure how many of you understood this or have difficulties. Please don't hesitate to ask. This is very, very important. Otherwise, I cannot go on further. Now, who will answer me first? Oh, Gunjit. Hello, Gunjit. There should be a way to check whether the guys are active or not active. I don't know how. Maybe I should ask Katre. Hello, Katre. I don't know. Maybe he is logged in and gone. What about Himanshu? Himanshu, are you there? Hello, Roshni.
Yes, sir.
Is it clear to you?
Yes, sir. I have to go through it once again, but it will be clear.
Your voice is splitting.
Yes, sir, it is clear. For now, I will go it once again, and if I have any difficulty, I'll get back.
Okay. And it is always good to come for the next lecture by reading the earlier lectures. Otherwise, when it accumulates, things become more difficult. Okay, now, who is, let me ask furthermore. Shivani. Shivani, are you there? I don't know how many people are you teaching. How about Sonakshi? Hello,
Yes, sir.
Sonakshi. Is it clear or not?
Yes, sir.
You are reluctantly saying yes, sir.
S-
But at least I am happy that you are answering. And if you have difficulty and you ask the difficulty, I'll be even more happier. So,
Hello, sir.
yes, please, who is it?
Sir, Rohitesh Pradhan.
Rohitesh, tell me.
So please one more time explain how you get F from the definition of F naught.
F is given to you, right? And what are you assuming?
Assuming that F naught is K-linear.
Yes, very good. Right? And
Yes.
what is the definition we have given F? We have given this. Look here. F is affine if and only if this.
Yes, sir.
In this, I am going to take P. P, I have taken the point P, right?
Yes,
So
sir.
that means isn't P is X plus P naught for some X?
Yes, sir.
Because
F naught is F is affine because F is affine.
no, that F is affine that you want to prove.
Oh, sorry, sir.
See here, I have written in a pink. P, only thing you have given is P, pointing E. And I say, look at P naught P arrow. And I called it. Then I say P has to be X plus P naught. Why that? Because E is an affine space.
Yes, sir. For every point we get a
E is an affine space. So
okay.
therefore the action of V plus is transitive.
Yes, sir.
That means P and P naught will belong to the same orbit.
Yes, sir.
Therefore it is this. And once it is this, now look what I have given. I have given F naught X is equal to F of P naught times F of X plus P naught an arrow. Isn't that means that this is my X? So in the process I erase that. P naught P. Right?
Yes,
very,
sir.
very simple. If you that's what I said. The key is this page definition.
Yes.
And once you understand this writing definition, then you can close your eyes and keep writing it.
Yes.
All right. Anything else?
Yes, sir. No, sir.
And then the remaining part is just writing correctly. And that I thought that you are used to it from your school days, college days, but looks like that you have forgotten. What about Shashank? Shashank Kumar Shukla. Are you there?
Yes, sir.
Yeah. What about you? How much are you understanding?
Yes, sir. Actually, sir, yesterday in last lecture I was not in class, so I am facing a little bit trouble in this affine connection and all. I will revise then.
But you are attending all the lectures?
Yes, sir.
All
Actually,
the lectures means my lectures at least.
Yes, sir.
Are you attempting the exercises?
Yes, sir. In starting, I have attempted exercises of group action, but not from this topics. I will try, sir.
Where are you from?
Sir, I am currently doing PhD in Rajiv Gandhi Institute of Petroleum Technology in Amethi, sir.
Where?
Amethi.
Amethi?
UP. Yes, sir, UP.
In Delhi or where?
In UP, sir, Uttar Pradesh.
All right. So
Yes, sir.
now is this clear that how do we check the map is affine or not? You have only given this condition. This condition given is on the linear map, linear part of that. It will be linear part of that. So given a vector space, linear map, and a point in V, point in E, if you have this equation, you can define a F map. This is similar to the what you said. Somebody said, no, how do we define linear map from a given vector space V to W? You choose a vector space basis and map those basis elements to arbitrary elements in the other vector space. And then you get a linear map. This is very, very part of it. All right. Now the theorem. This theorem is like producing linear maps. So you have combined many things now. So please read the statement of the theorem. As always I say, first try to understand a statement. If you don't understand a statement, you cannot attempt to prove it. And that's what happened most of the time. Most of the people don't understand a problem and then embark on the solutions. And they see it's very difficult. How can it be? You don't understand a problem, then how can you solve it? All right, so what is the theorem? E and F affine spaces over a vector space V and W. And remember here, I write my sentences complete. So even when you make your notes, you should write completely. Don't write shorthand. Don't make a messages like WhatsApp messages. Because if you do that, you yourself will not understand after 1 week. And this program is also, we also have this thing in mind that all of you are supposed to be PhD students or going to make a PhD in mathematics, and you should have a practice for writing also. It doesn't come automatically. All right, so what is the theorem? E and F affine spaces over a vector space V and W respectively, and I have given a point P naught in E and Q naught in E, and arbitrary I have given. And also I have given F naught. F naught is a linear map from V to W, and you know that there are many linear maps from V to W that we know how to produce. Then there exists a unique affine map F from E to F, which maps P naught to Q naught, and F naught is a linear part of F. How nice it is. So this will produce many affine maps from E to F. Okay, unique. First I am explaining unique, why it is unique. So I am simply giving a formula for F of P. In terms of what? In terms of that F naught and in terms of F of P naught. Because I want F of P naught to go to Q naught. So if you want, I am giving a formula for F, definition of F in terms of P naught, Q naught, and F naught. And that it is. I have written it. For arbitrary P. And again, the funda is very simple. You see here, if you have to draw the picture, what you do? You have given P naught here. And this P is arbitrary. And we know by definition of an affine space, this vector is P naught P. And the unique vector X. We join this. And definition of affine demands this equality. So it is, you can guess it from there. You can guess from this. See, this is the demand. This is a demand. This is P naught here, and then so you are this, not that where it came from. It came from the definition. So this proves that F is unique. If I know F naught, if I know image of P naught. That clear? Moreover, the above equation also proves the existence of F as affine by above proposition. So now you see here, what was the proposition? If I have given this formula, then already I know there is F is affine. All right, if you see my philosophy so far, my proofs are not longer, but the definitions are stronger. Examples are motivating, examples are also there. So that makes the proof simpler. Statements are preciser. All right, what is the immediate corollary? If E and F are affine spaces over V and W respectively, and if I have given an affine basis of E, then for every family Qi of points in F, there exists a unique affine map from E to F which map the point Pi to Qi. This corollary is same. We know it for vector spaces. And instead of affine, you say basis. There it is easy, but here you have to say affine basis. Now, what does affine basis means? So I have digressed you for the affine basis in the earlier lecture. Let me just earlier lecture no. So that is 5. Is it here? No, it is not here. So it must be in 6. No, it is 6 only, no? So it must be above. Here. So what is an affine basis means? So let us read there only. I have recalled it there. Here. What is an affine basis? So let us recall that first, and once we will follow from the corollary. Since I wrote it as a corollary to the theorem, it should follow from theorem immediately. So recall that points Pi, I in I is an affine basis of E. That means if I fix one of the point and take the vectors joining this point and the other points and call it Xi, then that Xi should be a basis of V. And see, imagine now 3-dimensional case, there will be 3 points, that is P1, P2, P3, and I have chosen this I naught as P2. And then what does it mean? This vector and this vector, they will generate a 2-dimensional vector space. That is our V. This is the plane, and nothing special about. So it's plane, therefore you need 3 points. And now one might ask a question. Does it depend on the point I choose? That I naught I choose? It should not depend. Because if I choose this P1, then I will have these vectors. That should mean it is a basis. But for better understanding, so why am I raising this point is because this will lead to some other thing which I don't want to discuss more. Right now we need this much only. So that means these 2 vectors should generate your vector space, or it should be a basis. Then you call it an affine basis. And now what does it say? I want to define map E to F, which is unique, which maps Pi to Qi. But what is that? That is precisely in the theorem. Theorem says if I give you a linear map, so I give you that linear map. That linear map should map this xi to some other wi, arbitrary wi, because this xi is the basis. And there exists such a field and unique. And if you translate it, what does it mean? Where Pi will go to Qi. That will give you this condition will ensure that. Because image of if P naught goes to Q naught, what is the image of how if P naught and if P naught and Fp naught are related? They are related by this. And therefore we achieve what we want. Alright, so you have to go through it. Then only you have to spend some time. It will not happen automatically that you can get all these things. Alright, so that proves the corollary, and that is what the lecture finishes here. That lecture, last lecture. Now we start the next one. That is 7. Now with this I want to describe the affine group. So once again, what is an affine group? I have recalled it here. I want to describe that more group theoretic way. So far we have described, if you want to say, you have described it geometrically. Now I will describe it algebraically. So it is a set of all affinities of E. What is an affinity? It's a affine automorphism of E. It's a map from E to E, and it's affine, and it is bijective. And F naught is linear part of it. And we have seen if F is bijective, F naught is also bijective. Therefore, F naught is actually an automorphism of the vector space V. And that we have denoted by odd K or GLK. And you know this group fairly better. So I have written somewhere that you'll see. So I want to relate automorphism group of V to the affine group of E. And what do I say? I define a map from the affine group of E to the automorphism. The map is very clear. If you have an affine automorphism of E, I just take the linear part of that. And we know linear part is uniquely determined, so this is indeed a map. And also the earlier theorem says this map is surjective. Means what? Given an automorphism of vector space V, I can define a map E, F. So that was precisely why I make a fuss about this theorem. Here, given F naught, and I can choose point P naught in E and Q naught in F. That I can choose. There are points there because E and F are non-empty sets, because they are transitive. The actions on them are transitive, so therefore they cannot be empty. So therefore definitely there is at least one point in each one of them. And then I use this P naught in E, Q naught in F, and a linear map F naught. Then with that, the theorem says I can define a unique affine map from E to F. That is why it is so important. So that shows this map is surjective. And I wrote 1 here. So all these groups are written multiplicatively. They are compositions. And they are not abelian groups. So identities, there are identity maps. Therefore it is denoted 1 here. And this means this arrow 1 here means this map is surjective. Are you aware of what are exact sequences? Hello, can somebody answer? I want to prove this sequence is exact. I told you this map and I will tell you this first map also. Can you please answer, Sonakshi? Hello, Sonakshi. She also decided not to answer. So whom can I ask? Can somebody talk or should I stop talking? I will stop talking.
No, sir.
Sonakshi.
Yes, sir.
Rohini, no, what is Rohini? No, Roshini. Roshini, you know what the exact sequence of group means? Groups.
Yes, exact sequence or
Short
what
exact
is
sequence.
the short exact sequence, wherein the kernel of the earlier one is equal to the image of the next.
Kernel of the later one.
Yeah, the kernel of the
Kernel
later one is equal to the image of the previous.
Image of this one. And this map is injective and this map is surjective. Then you call the sequence to be exact. Right? Also, please note that we are dependent on the fact that you are aware of some prerequisites and we cannot just go back and start doing them. And you would have, when you would have applied, you would have noted that we are demanding that you know, I don't know how many, 1, 2, 3, 4, 5 chapters of similar to that RT. So you know the basics of linear algebra, basics of groups, group homomorphism, group automorphism, and so on and so on and so on. And more than that, I am more disturbed because none of you talk. So it is not that we want to call you and we want to teach you. Of course, that we want to do that, but at the same time, your cooperation is more important. So if you are not going to reply, then I will stop. I have no interest in teaching. All right, it is my time is also coming to end. So please reply to this. If this is the last call I am making, otherwise I am going to stop.
No, sir. We know exact sequences of groups.
You know.
I know.
You know it. So why don't you guys reply?
Sir, you asked by name, so I thought.
I said anybody. How many people talk in a class actually?
Yes, sir.
I keep asking few names who so far replied. All right, so what are the maps? This map I have already given, if going to the linear part, and this T is I have written down. That's the group of translations of E. They are the maps E to E, and vector Y is given, and then you translated this E by P going to Y plus P. And earlier lecture also I have mentioned this. These form a group under composition. And you see here I have checked that also. This is the definition given. So they form a group, and that group is not different from the V plus. It is isomorphic to V plus. And that is the isomorphism also given. That Y going to Ty. This is an isomorphism. So both these groups, TE and this OT V, they are well understood groups. That is what I have written here. Both the groups OT V and T of U are well understood. And I want to make, so the philosophy is I know this group well, I know this group well, and therefore I want to understand the middle one better. And it follows that the image of this group is kernel of this group? That again precisely the theorem. this theorem on page 0611, this theorem that tells you that sequence is exact. That precisely, so I've written that reference. The theorem on page L0611. From that it follows that this quotient group, so it's a normal subgroup because it's a kernel of this map. Kernel of a group homomorphism is always a normal subgroup. Therefore, the quotient group makes sense. And this quotient group, because this map is surjective, the first fundamental theorem in groups that will tell you this is isomorphic to the automorphism. And I have also given 2 examples. What happens when you take E be an affine space over V and you have one point fix that you have chosen that as the origin, let us say. Then I am defining a map from the automorphisms of V to this affine group. What is linear part goes to all those affinities where F0 is their linear part and the point 0 is fixed under F. So I have not taken all, but all those affinities where this is a fixed point. So that set is denoted by A0 T. So there should be A0 here. A0 means AO. O is fixed. So they are all affinities of E where O is fixed. That's it. And F0 is the linear. So what is the image of this map? AO, what is AO precisely? All that sort of thing. All those F in this where O is a fixed point of F, and there are affine collineation which maps O to O. So that serves O as a purpose, O as the origin. So I can draw vectors from that O to any other point. This and what is the, if I take V any vector space and think V as a affine space over V itself, then AV is understood better. That because it's all those map V to V, so Fx is a linear part plus they're translated by that X0. So what is varying is F0 is varying and X0 is varying. So that is the affine group of V. And what I am going to prove is this affine group is nothing but V symmetric product automorphism. So I have to therefore understand what is a semi-direct product. And I wanted to do that, but unfortunately I didn't reach it. That is what the title of this lecture I wanted. Affine group and semi-direct product.